Welcome to qnawire.
Hi, so for this problem, the first thing that you need to remember is that the E0 for the cell is going to be equal to E0 of the cathode minus E0 for the anode. And both of these, the potentials are taken from their reduction reactions. The origin of this minus sign comes from the fact that we switch up the equation of the anode because we're going to have an oxidation. But since in the tables we are going to have always the reduction potentials, this is the way that we can find directly the E0 for the cell by just looking at the tables. So, out of the possible options that we're going to have, in the case for the cathode, remember that in the cathode occurs the reduction. So, the reaction that we're going to employ for the cathode, it is going to be silver plus one electron, producing silver solid. And the potential for this case is 0. It's going to be 0.8 volts. Okay. Now for the anode, the equation that we're going to use, it is going to be that of zinc, but we need to switch it up. So we're going to have zinc solid that is going to turn into zinc 2 plus 2 electrons. And the E0 for that cell corresponds to minus 0.76. E0 for reduction. Okay. If we did the E0 for the oxidation, you would need to have the opposite value. So to find an E0 of that cell, the value is going to be 0.8 volts minus 0.76 volts, which is going to give us the desired 1.56 volts. Here you may realize that for this to be to be balanced, you would need to multiply the equation of the cathode by 2 to get the overall reaction. But remember that the E0 potentials are not going to depend on the number that you need to multiply that equation. They are independent of the stoichiometry. Okay? So now the diagram that we are going to use, let's draw two different flasks. Each of them are going to have a solution. First of all, on the left hand side, we're going to write down the anode. And I'm going to draw in purple a bar of zinc. Okay. So on the left side, we're going to have here a zinc bar. On the right side, we're going to have a gold one. Oh, sorry, a silver one. Silver one solid. And in between, connecting them, we need to draw a salt bridge. Okay. And finally, in order to be able to measure what is happening here, we need to get a voltmeter. And the flow of electrons goes in this direction. So this is going to be our diagram. Remember that here the oxidation reaction occurs, over here the reduction, because this side corresponds to the cathode. So this is the answer for part A. Next up, for B, we need to identify the redox reactions at each of the electrodes that we are going to have. So we already identified what are the corresponding reactions. So just in the zinc electrode, we're going to be our anode, and the redox reaction is going to be the one that we see on the top. Zinc solid produces Zn2 plus 2 electrons. Now, in the cathode, we're going to see our oxidation. So that is going to be, in the cathode, we're going to have our reduction of silver, and the overall reaction is going to be, we need to multiply the one that we have on the top by 2 to have the balance equations. In both of the cases. Okay. Just as a reminder, anode oxidation, cathode reduction. Finally, writing this down in the electrochemical cell notation, we're going to have zinc solid, Zn2 plus, silver plus, silver solid. And now, for the final part, we know that using our table, we need to explain why the gold ions are not normally found in aqueous solution. And the way to do it is by looking at the two potentials that are right next to each other. H plus 2 electrons produces water. This one has a potential of 1.23. And the other one that we are interested in is going to be gold plus 1 electron. It is going to produce gold solid at a potential of 1.68. So what is going to happen with gold in water is that if we add up two times this equation, we add it to the inverse of my other reaction, H2O liquid produces 1/2 O2 gas plus 2H plus 2 electrons. What we are going to get is that, two equivalents of gold plus water in liquid. It's going to produce two equivalents of solid gold plus 1/2 of oxygen gas plus two equivalents of hydronium ions in solution. And the E0 for this reaction, it is going to be 1.68 volts coming from the gold reaction minus 1.23 coming from the water reaction. Here we don't need to know the number, we only by identifying that the E0 for the cell is larger than 0 is enough, because we know that delta G naught of the reaction is going to be equal to minus NF times E0 of the cell. This implies that delta G for this reaction is going to be lower than 0. Thus, gold plus ions spontaneously convert to solid gold in water. So we're going to have the spontaneous reduction of gold when we are in water. And that would be all.